So, what we are going to do in the next 12 weeks is to talk about each and every component that I said in the previous slide and how that is used for that entire MPC to come together. Okay. And that is what I talked about in the course plan slide. I had broken down into 3 sections of 4 week modules. Each will come end of each of those sections, there will be quiz 1, quiz 2 and the final exam. Okay. And each of those 4 weeks will have a component about the model, will have a component about observer and will have a component about controller. Okay. And that is what we are going to do in the rest of this course. So, this was what I want to kind of talk about. This is again not, this part is not relevant with respect to implementing, but I really like to think about MPC in its historical sense. So, I have about 10 minutes. So, in the next 10 minutes, I will try to give a historical perspective. It will be a little bit quick, I will rush through the slides a bit. Okay. So, initiated in shell oil refineries, blah blah blah, I just talked about this. Okay. Yeah. So, IDCOM and DMC were the industrial implementations of MPC. Okay. All of these implementation use linear model. Okay. These 3 use what is known as convolution model. This one uses ARMA model, this one also uses convolution model. Okay. SMOC is an implementation that uses a state space model. Okay. Last week I had talked about 3 different types of models: state space, finite impulse and finite state response model, and transfer function models. Okay. We will talk about, and the reason why I am going to talk about all those 3 models is at some point or the other all of these models have been used historically in industrial MPC. Okay. The theoretical pinning of MPC was when people in 1980s started combining it with the concepts, theoretical concepts in linear optimal control, and that is what we are going to talk about in week 5 to 8. In week 5 to 8 we will talk about linear optimal control theory. Week 9 to 12 we will combine the stuff that we have talked about, MPC and modeling and so on, with the linear optimal control theory part. So, key developments in MPC, IDCOM was the first implementation, followed by DMC. DMC stands for dynamic matrix control. Okay. The term dynamic basically means that it was using dynamic models or models that can predict the future behavior. Okay. State space MPC came in late 1980s, and that was around 1986 or 88 was when state space MPC came. Extension to nonlinear systems in mid 1990s. Okay. In around 2000 or 2001, a new development happened where people came up with explicit MPC. So, what explicit MPC does is, it does not, you are not solving the optimization problem online, but you are somehow taking pen and paper, let us say, and solving the optimization problem, and then a control chart people come up with, that if this is the state, then implement this control move, if this is the state, then implement this control move, this is the state, implement this control move. This particular development was of a lot of interest to mechanical engineering systems and so on, where people were used to using lookup tables. If this is the value, then do this, if this is the value, then do this, if this is the value, then do this. Okay. Explicit MPC tried to use best of both worlds, you can say it now. Okay. And around 2007ish there was distributed MPC. Before that, MPC calculations were done in a centralized computer, but now the questions being asked is, what if you let each individual unit determine the MPC control actions in a DCS system itself, in a distributed control system itself. The ones that I am showing as hollow circles, those are in my opinion major developments, and the one that I am showing below the line, those are relatively minor developments. It started off with a linear or linear optimization based objective function. Around early 1980s, quadratic optimization came in. Parallels with generalized process control came in 1983 or 84. Extension to infinite horizon case came in around 91 to 93 period, and that is where the question about what should the size of M be and so on comes in. Is should we have M as finite, should we have M as infinite, or can we use theory in order to keep M finite, but the solution will be infinite horizon optimal? That was the question that was asked over here. Late 90s robust control came in, mid 90s to late 90s robust control. Extension to batch systems also came around that time, and the ideas from AI literature called reinforcement learning or approximate dynamic programming, that came in early 2000s. Okay. Economic MPC came in about 10 years back, where you combine the real time optimization layer with the APC layer to do optimization in the APC layer itself. Yeah, so what were the various inputs from various theories that came in the history of MPC? As I said, that IDCOM and DMC, they did not have a whole lot of theory. It was basically a few really smart engineers in industry. They came together and figured out how to solve a problem using this MPC framework. Okay. The theory in linear quadratic optimal control started being used in early 80s, and that is what gave rise to using quadratic optimization in MPC. Quadratic optimization is the one that you saw earlier, summation RA minus RA set point squared plus RB plus Q, that is the quadratic optimization problem. Okay. Again in 1980s, the quadratic optimization was used for finite step response and finite impulse response models. State space models started being used in late 80s. Okay. And again the development over there was motivated by theory in LQR. Okay. And again the LQR theory was used in determining this infinite horizon control problem. And again this LQR theory was used once again for explicit MPC. Okay. GPC on the other hand did not come, the origins of GPC is not from optimal control viewpoint, but it is from adaptive control viewpoint. Separately, there was a completely different branch called robust control, which said that, you know what, whatever you assume about your process, it is not perfect. Those assumptions are not perfect, that knowledge is not perfect. In presence of imperfections, what is the worst that could happen? So, let us design the controller not to do the best, but also to prevent the worst case scenarios. That was the idea behind robust control. The ideas of robust control started being implemented in MPC by bringing in those ideas and merging with the ideas of MPC. That happened late 1990s. So, what were the driving factors behind this? Okay. So, the driving factors behind the initial ones were using a step response matrix. We started with a linear objective function, that means maximizing the product. Okay. How to maximize the total amount of ethylene that comes out of that system. That was the original objective function in IDCOM and DMC. Okay. Then quadratic optimization function came in. How do we meet the set point in the best way? Because these were step response models, they were determined using step tests in the industry. What those step response models are, we are going to come in week number 2. Okay. How to identify them from step tests, we will come to that in week number 4. Okay. So, what does step response model mean? Is you give a step change in the input, that is shown in blue over here. Okay. And see how the process is responding. This is the response of the process, and you are going to use the values S1, S2, S3, S4 up to Sn as a part of your model. Okay. So, the idea over here in step response model is something called superposition. So, let us say you have an input move that looks like this. This input move is nothing but summation of this step plus this step plus this step in the negative direction plus this step. Okay. Because it is linear, superposition holds, which means the response of each of these input moves, this is a unit step. So, response was what we saw in the previous slide. This is let us say half a step. So, the response is just half multiplied by S1, S2, S3, and it has been delayed by 1 time unit. Why? Because input has been shifted by 1 time unit. Okay. This is a negative unit step. So, the response is minus S1, minus S2, minus S3, minus S4, but it is shifted by 2 time steps. Why? Because this does not come in at time 0, it comes at time 2. Okay. This is a half step that is coming at time 3. Because it is linear, you multiply by half, because it comes at time 3, you shift it by 3 time steps and you see this out. Okay. So, the output, the net output of this series of steps that you see over here in blue is nothing but this guy plus this guy plus this guy plus this guy. That is the concept behind step response models. Okay. So, this is how you predict the future. Okay. And this was what was used in DMC and QDMC. The step response models was used in DMC, the idea was linear objective function, QDMC the idea was quadratic objective functions. Okay. And how did they implement receding horizon control? This is the thing that we saw earlier. This is where we reached. So, what do you do at next time? At next time you say that there is an inaccuracy in the model. Okay. So, I am just going to shift my model. Oh, okay, that did not work. So, I am just going to shift my model by the same amount. So, because you have reached over here, you are just going to shift the prediction by that same amount. That is what was said in the industrial implementation. What we will do in week 6 of this course is to show how this industrial implementation, how very nice and theoretically solid it was. Okay. People at that time did not bring in theory into it, but in this course we will bring in theory to say why doing this was actually such a good idea for step response models. That is something that we will do in week 6. Okay. Yeah, so this is just summarizing this, that it originated in the industry, used experimentally obtained step response model, linear objective function was originally used, and then we moved on to quadratic objective functions. Okay. So, that is the summary of DMC, something that we will do in week 1 to week 4 of this course. Thereafter, LQR inputs got used in MPC in order to do state space MPC and infinite horizon. Parallelly, estimation theory was developed, and that is known as Kalman filter, and that started being used. Okay. And in week 5 to week 8 of this course, we are going to do Kalman filter followed by LQR. Week 8 we will do how LQR feeds into state space MPC, and we will talk about state space MPC from week 9 onwards. Okay. And for state space MPC, this is the state space model that we are going to use. Okay. So, and we are going to determine how the future predictions using state space models is going to be, all of these things we are going to do. And the state space MPC, the prediction of the future looks similar to step response MPC with small amount of differences, and what those things are we are going to talk about. Yeah, oh, this is that slide where we are talking about. Okay. This is where you have reached, this is what we have talked about before, this is what receding horizon means. And what do you do when your predictions do not match, the model predictions do not match the reality? Simply what you are going to do is move this over here, and in week 6 we are going to look at how doing this is actually a nice thing to do as well. Okay. Okay, and we will finish off with talking about just the popularity of MPC, its integrated solution, systematic methodology and efficient utilization of degrees of freedom. This is the summary slide that I will end this lecture with. Okay. The other reason why I wanted to cover this history is you will notice from the history you go and now take a look at the outline of this course. The outline of the course roughly follows the historical footsteps that MPC took. I like to do a course in this particular manner, which is probably a little bit different than other MPC versions of this course. I like to do it this way because history also tells us something. There was a reason why historically it went in this direction. So, that is the reason why I also wanted to cover the history.